Beneath our feet, something extraordinary is happening. In a specific region of the world, the ground is not just shifting, it's rising at an alarming rate. Scientists have been tracking this phenomenon for years, but recently, the rate of uplift has accelerated beyond anything previously recorded. The implications of this are vast, sparking concern among geologists, seismologists, and even climate scientists. Is this the precursor to a massive geological event? Could it signal the reawakening of a dormant force hidden beneath the Earth's crust? At first, subtle changes went unnoticed. Satellite data showed slight anomalies, but nothing that warranted immediate concern. Over time, however, GPS monitoring stations detected a consistent pattern. The ground was moving upward, sometimes by several inches per year. In some areas, the rate of uplift had doubled in just a few months, suggesting an enormous force at play. One of the leading theories points to magmatic activity deep within the Earth. Volcanic systems don't always announce their presence with dramatic eruptions. Sometimes, their movements are silent yet incredibly powerful. When magma begins pooling beneath the surface, it can create immense pressure, forcing the land above it to bulge. Historically, this type of inflation has preceded volcanic eruptions, but the current situation is unique. The rise is happening over a vast area, much larger than what is typically seen before an eruption. This suggests an underground system that is far more complex than a single volcanic conduit. If a new volcanic system is forming, the consequences could be severe. Volcanologists have pointed to past instances where rapid ground inflation led to cataclysmic eruptions. For example, before the massive eruption of Mount St. Helens in 1980, the northern flank of the mountain began to bulge outward due to the intrusion of magma. What followed was one of the most violent volcanic events in modern history. If a similar mechanism is at play here, but on a larger scale, the results could be even more devastating. But not all scientists are convinced that magma is the culprit. Some argue that the cause could be linked to deep-seated tectonic shifts. The Earth's crust is not a static shell, it's a constantly moving, shifting, and evolving structure. When sections of the crust experience unusual pressure, they can lift, causing the land above to rise. This is often seen in areas of active plate boundaries, where tectonic plates grind against one another, creating a buildup of stress. If this uplift is being caused by a hidden fault system or an undiscovered rift, the implications could extend beyond just this one region. Further complicating matters is the presence of geothermal anomalies. In certain parts of the rising landscape, surface temperatures have increased by several degrees, hinting at the movement of heated fluids below. This could indicate the presence of a hydrothermal system, underground reservoirs of superheated water that interact with geological formations. Hydrothermal activity is often associated with seismic unrest, as the movement of heated water can weaken rock structures and trigger instability. Historically, regions with significant uplift have experienced dramatic transformations. In the Afar Triangle of East Africa, parts of the land are gradually splitting apart as a new ocean basin begins to form. There, the ground has risen and cracked, slowly reshaping the landscape over millions of years. But what makes the current situation so alarming is the speed at which it's happening. Instead of gradual shifts occurring over geological timescales, the changes being observed now are happening within a human lifetime. With each passing month, new data pours in, revealing more clues about what might be unfolding beneath the surface. But the deeper scientists look, the more questions arise. Could this be the early stages of a supervolcanic formation? Is an unseen fault line preparing for a massive rupture? Or is this an entirely new phenomenon that challenges our current understanding of Earth's dynamic processes? One thing is certain, the ground beneath us is far from still, and whatever is happening here may only be the beginning. Beneath the Earth's surface, vast reservoirs of molten rock churn and shift, their movements hidden from human eyes until their effects become impossible to ignore. When the ground rises at an accelerated rate, one of the most likely culprits is magmatic activity, an underground process that can remain silent for centuries before suddenly making its presence known. Magma is not just a static pool of molten rock. It is an incredibly dynamic force, expanding, contracting, and pushing against the surrounding crust. As it rises from deep within the mantle, it collects in underground chambers, slowly accumulating in volume. The pressure builds, and with nowhere else to go, the ground above begins to lift. This process, known as magmatic intrusion, has been observed in various volcanic regions around the world, including Yellowstone National Park, where the ground has risen and fallen over the years due to the immense magma chamber lurking beneath. But what's happening here appears to be unfolding at an even faster rate, raising concerns that something larger is brewing beneath the surface. The presence of harmonic tremors, long-lasting seismic vibrations that indicate the movement of magma, suggests that molten rock is actively flowing into new chambers underground. Unlike standard earthquakes, which create short bursts of energy, harmonic tremors produce a continuous, rhythmic shaking, a telltale sign that something is shifting deep below. This could be the early stages of a much larger geological event, one that scientists are scrambling to understand before it escalates into something catastrophic. The scale of this uplift is what has experts most concerned. If magma is actively accumulating in a vast underground chamber, the question then becomes, how large is it? Some geologists fear that this could be the formation of a supervolcano, a massive volcanic system capable of global consequences. Supervolcanoes don't erupt frequently, but when they do, the results are devastating. The last known supervolcanic eruption occurred around 74,000 years ago, when Indonesia's Toba caldera exploded, releasing enough ash into the atmosphere to trigger a volcanic winter that nearly wiped out early human populations. While there's no definitive evidence yet that this uplift is leading toward a supervolcanic eruption, the rapid pace at which the ground is rising suggests that something extraordinary is taking place beneath the surface. Heat signatures detected from satellite imaging reveal rising surface temperatures in the affected area. A subtle but measurable increase in heat could mean that magma is inching closer to the surface, slowly warming the rock above it. Alongside this, increased emissions of sulfur dioxide and carbon dioxide suggest that molten rock is degassing below the ground. These emissions often serve as an early warning sign, an indication that volcanic activity could be on the horizon. But without a clear volcanic vent, the question remains, is this a new volcanic system forming, or is the crust itself undergoing a transformation unlike anything recorded before? History provides us with several examples of similar events, some of which resulted in catastrophic eruptions, while others remain geological curiosities. In 1994, the Rabaul caldera in Papua New Guinea showed significant ground deformation before finally erupting, covering the city of Rabaul in thick layers of ash. In the 1980s, Italy's Campi Flegrei caldera experienced rapid uplift, forcing thousands of residents to evacuate in fear of an impending eruption. However, there are also cases where uplift occurs without a resulting explosion. Long Valley caldera in California has been inflating for decades, with magma slowly pooling underground but never breaking through the surface. Not all cases of magmatic uplift lead to eruptions. Sometimes, magma rises but never reaches the surface, instead cooling and solidifying underground. These failed eruptions leave their mark, permanently altering the landscape. Could this be one of those cases? Or is this only the beginning of something much bigger? The next steps in research are critical. Scientists are considering deep drilling projects to extract samples directly from beneath the uplifted area, hoping to determine the temperature, composition, and movement of the magma below. Meanwhile, satellite-based radar imaging continues to track changes in elevation, providing a real-time view of the shifting landscape. The data being gathered now could be the key to understanding whether this region is on the verge of a geological breakthrough or an impending disaster. If magma continues to push upward, this could be the early stages of a new volcanic giant forming beneath the Earth's surface. But if this uplift is caused by something else, something yet to be fully understood, then humanity may be witnessing a geological process unlike anything ever recorded. Beneath the surface, magma is not just a static pool of molten rock, it is a dynamic, constantly shifting force that influences the very shape of our planet. The movement of magma plays a crucial role in the phenomenon we are witnessing, and understanding its behavior is key to determining the cause of the rapid ground uplift. Magma does not move in a uniform or predictable way. It can accumulate in vast underground chambers, forming reservoirs that can span tens or even hundreds of miles. These reservoirs are not just simple pockets of molten rock. They are complex, layered structures where different types of magma can mix and interact over time. The composition of the magma itself plays a major role in how it behaves. Some types are highly viscous, meaning they move slowly, trapping gases and building pressure over time. Others are more fluid, capable of moving through cracks and fissures with relative ease. One of the most concerning aspects of the current uplift is the sheer volume of magma that could be accumulating beneath the surface. If a deep magma chamber is feeding into a shallower reservoir, pressure could be increasing at an alarming rate. This buildup can cause the surrounding rock to crack and fracture, allowing more magma to seep into new spaces and further contributing to the expansion of the ground above. In some cases, these fractures can extend for miles, forming intricate networks of underground conduits that transport magma to entirely new locations. Seismic activity in the area provides further evidence that magma is on the move. Small, repetitive tremors, often referred to as harmonic tremors, are a classic indicator of magma pushing its way through the crust. These tremors are different from regular earthquakes, which result from sudden shifts along fault lines. Instead, harmonic tremors produce a continuous vibration, almost like the deep, resonant hum of a massive engine running beneath the surface. Scientists have detected an increase in these tremors, suggesting that magma is actively rising, searching for an outlet. The composition of gases escaping from the ground further supports this theory. Magma contains a mix of volatile gases, including carbon dioxide, sulfur dioxide, and water vapor. When magma nears the surface, these gases begin to escape through cracks in the rock, sometimes forming visible fumaroles, steam vents that release plumes of gas into the air. A sudden spike in sulfur dioxide emissions is often a sign that magma is approaching the surface. In the region experiencing uplift, researchers have recorded increasing concentrations of these gases, indicating that the underground system is becoming more active. But perhaps the most troubling sign of all is the deformation pattern itself. In some cases, ground uplift occurs in a relatively uniform manner, like a balloon slowly inflating. However, the pattern observed here is more complex. Certain areas are rising faster than others, creating a warped, uneven landscape. This suggests that multiple sources of pressure are at work, possibly indicating the presence of more than one magma chamber. If these chambers begin to interact with each other, the situation could become far more volatile than previously anticipated. One particularly troubling possibility is that the magma intrusion could eventually lead to the formation of a new volcanic vent. While many people think of volcanoes as towering mountains, new vents can form in unexpected locations, even in relatively flat terrain. These vents often start as small fissures, but as pressure builds, they can expand rapidly, spewing lava, ash, and toxic gases. If a new vent were to form in a populated area, the consequences could be catastrophic. To further complicate matters, the region experiencing uplift is not isolated from other geological systems. Underground, magma can interact with vast networks of faults and fractures, influencing seismic activity across a much larger area. If enough pressure builds up, it could even trigger a significant earthquake, releasing energy that has been accumulating for centuries. This raises the question: is the uplift itself the primary concern, or is it a symptom of a much larger, interconnected geological process? Scientists are racing to answer this question. Using advanced satellite imagery, they are tracking minute changes in ground elevation with incredible precision. Every millimeter of movement is recorded and analyzed, providing a clearer picture of how the land is changing over time. But even with these tools, predicting the outcome remains a daunting challenge. Geological processes operate on timescales that can span thousands, even millions of years. What appears to be an imminent event could still be centuries away, or it could unfold within our lifetime. The implications of this uplift extend beyond just one region. If magma activity is intensifying on a global scale, it could signify a shift in the Earth's internal dynamics. Some researchers speculate that changes in the planet's core, or variations in mantle convection, could be driving increased volcanic activity worldwide. If true, the rising ground we see today might be just one symptom of a much larger planetary process, one that could have far-reaching consequences for the future of our world. Deep beneath the Earth's surface, massive tectonic forces are constantly at work, shifting and reshaping the very foundation of our planet. These movements are typically slow, measured in millimeters per year, but when they accelerate or change direction unexpectedly, the effects can be profound. The rapid ground uplift we are witnessing may be linked to a deep-seated tectonic shift, an event that has the potential to disrupt entire continents, trigger massive earthquakes, and even alter global climate patterns. Tectonic plates are not rigid, unyielding slabs of rock. They are immense, floating sections of Earth's lithosphere that move atop the semi-fluid asthenosphere below. The driving force behind their movement is the slow churning of molten rock deep within the mantle, known as mantle convection. However, this process is far from uniform. Certain areas of the mantle exhibit sudden shifts in temperature and pressure, leading to unexpected movements in the plates above. When these deep forces intensify, entire regions can experience sudden ground uplift or subsidence, sometimes by several meters in a matter of years. Recent geological surveys suggest that the current uplift may be connected to a shift occurring deep within the Earth's crust, possibly at depths exceeding 100 kilometers. This is well below the typical depth of earthquake activity, which usually occurs in the upper 30 to 50 kilometers of the crust. What makes this shift particularly concerning is its location, near a boundary where two tectonic plates are locked in a slow but persistent struggle. If stress is building along this boundary, the consequences could be far-reaching. One of the most well-documented cases of deep-seated tectonic shifts influencing ground elevation occurred in the Andes Mountains. Over the course of several decades, certain regions of the Andes have been rising at an accelerated rate, sometimes by as much as 10 millimeters per year. This uplift is not due to volcanic activity, but rather the slow collision of the South American and Nazca plates. However, unlike the gradual uplift seen in the Andes, the current phenomenon we are observing is occurring much more rapidly, suggesting a more immediate source of pressure deep within the Earth. Seismic data from the region undergoing uplift reveals an unusual pattern of deep tremors. Unlike traditional earthquakes, which release energy in sudden bursts, these deep tremors occur as a series of prolonged vibrations, sometimes lasting for hours or even days. This suggests that the crust is not simply breaking along a fault line but rather undergoing a gradual but powerful deformation from below. In some cases, these tremors precede major tectonic shifts by months or even years, acting as an early warning system for geologists monitoring the region. A particularly alarming possibility is that we may be witnessing the early stages of a process known as delamination. This occurs when the lower portions of the continental crust become unstable and begin to sink into the mantle. As the heavier material descends, the lighter, more buoyant portions of the crust rise to compensate, leading to rapid uplift at the surface. If this is indeed happening, we may be looking at a long-term geological transformation, one that could permanently reshape the landscape. Another possibility is that the ground uplift is linked to a phenomenon known as tectonic rebound. This occurs when pressure that has been built up over centuries is suddenly released, allowing the land to rise as the crust readjusts. A famous example of this is found in Scandinavia, where the land has been slowly rising for thousands of years due to the melting of ancient glaciers. However, in our case, no glacial retreat is involved, meaning that some other force, possibly a deep tectonic shift, is responsible for the rapid change we are witnessing. Historical records indicate that similar ground uplift events have preceded some of the largest earthquakes in history. One such event occurred in Japan in the years leading up to the 2011 Tohoku earthquake. Small but persistent ground uplift was detected along the eastern coast of Japan, but at the time, scientists were unsure of its significance. When the magnitude 9.0 earthquake struck, it became clear that the uplift had been an early indicator of the immense stress that had been building along the subduction zone. If the current ground rise is a precursor to a similar event, the implications could be dire. The big question that remains is whether this tectonic shift is an isolated event or part of a larger pattern of planetary change. Some scientists suggest that we may be entering a period of increased tectonic activity, driven by changes deep within the Earth's interior. There is evidence to suggest that the outer core, which generates our planet's magnetic field, may be undergoing subtle shifts that, in turn, influence mantle convection and, ultimately, tectonic movement. If true, we may see more instances of unexpected ground uplift, seismic activity, and even new fault formations in the coming years. Right now, experts are closely monitoring the region, using satellite imagery, ground-based sensors, and seismic readings to track every millimeter of movement. If the rate of uplift continues to increase, it could indicate that a significant event is imminent. However, if the uplift stabilizes, it may suggest a slow and gradual tectonic shift rather than an impending catastrophe. For now, the forces deep beneath our feet remain a mystery, but one thing is certain: the Earth is restless, and its movements, no matter how slow or sudden, have the power to shape the future of our planet in ways we are only beginning to understand. While the exact cause of the rapid ground uplift remains uncertain, one thing is clear: this event is not happening in isolation. Similar shifts have been recorded in various parts of the world, suggesting that deep-seated tectonic forces may be more active now than at any point in recent history. But how does this fit into the larger picture of Earth's constantly shifting crust? One intriguing theory involves the concept of supercycles in plate tectonics. These cycles, which can span hundreds of millions of years, dictate the movement of Earth's continents and the rearrangement of its tectonic plates. Scientists believe we are currently in the middle of such a cycle, with old tectonic plates gradually being pushed aside as new fault lines form deep beneath the surface. If this is true, then the current uplift may be just one of many signs that a larger, more dramatic reconfiguration of Earth's crust is underway. Some geologists have even proposed that we are in the early stages of a process known as incipient rifting, where a new tectonic plate boundary is forming beneath our feet. This would mean that, over the course of millions of years, the land currently rising could eventually split apart, creating a rift valley similar to the East African Rift. The consequences of such a shift would be enormous, potentially leading to the formation of a new ocean basin where land once stood. While this may sound like a far-off scenario, some studies suggest that the processes that lead to rifting can unfold much more quickly than previously thought, especially when deep mantle forces are involved. Another possibility is that the deep-seated tectonic shifts responsible for the uplift are connected to ancient, long-dormant fault lines that are being reactivated. Throughout Earth's history, massive fault zones have formed and then seemingly gone quiet for millions of years, only to awaken suddenly under the right conditions. If a previously stable fault has become active again, it could explain why we are seeing such dramatic changes in elevation. One such example occurred in the New Madrid seismic zone in the central United States. While this region is far from any tectonic plate boundary, it experienced a series of massive earthquakes in the early 19th century, suggesting that deep, hidden faults can still unleash incredible energy when conditions align. If the current uplift is related to a similar type of reactivation, we may need to reassess which regions of the world are truly seismically stable. Interestingly, satellite data has revealed that the uplift is not occurring evenly across the affected region. Some areas are rising faster than others, which suggests that multiple geological processes may be interacting at once. In some places, the ground is bulging upward at an accelerated rate, while in others, it is shifting horizontally. This unusual pattern could mean that, rather than a single cause, we are dealing with a complex interplay of deep magmatic movement, shifting fault lines, and mantle convection. Even more concerning is the potential link between this ground uplift and the increase in seismic activity observed worldwide. In recent years, earthquakes have been occurring in places that were once considered geologically quiet. Some scientists argue that the entire planet is experiencing a period of heightened geological activity, one that may be driven by forces deep within Earth's core. Recent studies have suggested that fluctuations in the flow of Earth's outer core could influence the movement of the mantle above it, setting off chain reactions that impact tectonic activity. If this is the case, then the rapid ground uplift we are witnessing might not be an isolated event, but rather a symptom of a much larger planetary shift. Adding to the mystery is the fact that some of the regions experiencing uplift are also seeing an increase in geothermal activity. This suggests that heat from the mantle is playing a role in driving the movement of the crust. In some cases, rising magma could be forcing the land upward, while in others, superheated water trapped beneath the surface might be creating pockets of pressurized gas that are pushing against the rock layers above. One particularly compelling case study is the Yellowstone caldera, where ground uplift has been detected multiple times over the past several decades. In Yellowstone, the rising land is directly linked to the movement of magma beneath the surface. While the uplift we are currently observing may not be volcanic in nature, it is possible that similar processes are at play, with deep mantle plumes acting as a force beneath the crust. With so many variables at work, researchers are struggling to determine whether this uplift is part of a natural cycle or a precursor to a major seismic event. If it is the latter, the consequences could be significant. Large-scale ground uplift has preceded some of the most powerful earthquakes in history, and if the current trend continues, it could signal that the Earth's crust is preparing for a dramatic adjustment. Geologists are now deploying more sensors and monitoring equipment to better understand the situation. By measuring ground deformation in real time and analyzing seismic patterns, they hope to determine whether the uplift is slowing down, accelerating, or reaching a critical tipping point. Whatever the outcome, one thing is certain: the Earth's crust is in motion, and the forces at play may reshape our understanding of planetary dynamics in ways we have yet to fully comprehend. As researchers continue to monitor the rapid ground uplift, another critical aspect they are examining is the role of mantle convection, one of the most fundamental processes driving plate tectonics. Mantle convection occurs when heat from Earth's core causes the semi-molten rock of the mantle to move in vast, slow-moving currents. These movements, though imperceptible on a human timescale, have the power to reshape continents, generate massive earthquakes, and even alter climate patterns over millions of years. But what if, for some reason, this process has intensified in recent times? Some geophysicists propose that changes deep within the mantle may be accelerating the movement of tectonic plates, leading to the unexpected rise of land masses in certain regions. If the mantle beneath the affected area is experiencing an increase in heat flow, this could explain the upward motion we are witnessing. Such a process could be triggered by fluctuations in the core's temperature, increased radioactive decay in certain areas of the mantle, or the upwelling of deep-seated mantle plumes, columns of superheated rock that rise toward the surface. There is even speculation that the mantle itself may not be as uniform as we once thought. Recent seismic imaging studies have revealed the presence of vast, mysterious structures deep within the Earth, sometimes referred to as large low-shear velocity provinces, LLSVPs. These enormous regions of dense material sit at the boundary between the mantle and the core, and some scientists believe they could be influencing the movement of the Earth's crust in ways we are only beginning to understand. If one of these LSVPs is shifting, breaking apart, or interacting with mantle plumes, it could be causing a localized disturbance that manifests as rapid ground uplift. Another possibility being explored is the concept of deep earth tides. While we are familiar with the graviton iron in the outer core, however, this field is not static. It shifts, fluctuates, and even reverses entirely over long timescales. Some researchers believe that fluctuations in the field could be tied to changes in the flow of the core itself. If the core's motion is altering in a way that affects both the magnetic field and the mantle above it, it could be contributing to the unusual tectonic activity being observed. One of the most intriguing possibilities is that we are in the early stages of a magnetic pole reversal. These reversals have happened many times in Earth's history, and while they do not happen overnight, they are often accompanied by increased geological instability. If the core is indeed undergoing a shift that will eventually lead to a pole reversal, then the rapid ground uplift we are seeing could be just one of many symptoms of this profound planetary transformation. Meanwhile, satellite data has revealed another unexpected detail. The affected region is also experiencing changes in gravity. This suggests that mass distribution within the Earth is shifting, either due to deep geological processes or changes in underground reservoirs of magma or water. While variations in Earth's gravitational field are not unusual, the fact that they are occurring alongside significant ground uplift raises new questions about what is truly happening beneath our feet. Some researchers have drawn parallels to historical events where gravitational anomalies were recorded before major tectonic shifts. In some cases, such anomalies have preceded earthquakes or even large-scale land deformations. Could the current gravitational changes be an early warning sign of something larger to come? Another compelling angle in this unfolding mystery is the role of deep crustal fluids. Scientists have long suspected that vast reservoirs of water, brine, and even carbon dioxide exist miles beneath the Earth's surface, trapped within porous rock formations or locked away in mineral structures. These fluids play a crucial role in regulating seismic activity, influencing magma movement, and even affecting the buoyancy of the crust itself. But what happens if these deep fluids are suddenly mobilized? Some experts believe that a change in the pressure balance of these underground reservoirs could be contributing to the rapid uplift we are observing. One possible explanation is the release of high-pressure fluids from deep within the crust, causing a swelling effect as the rock above is forced upward. This can happen naturally due to long-term geological shifts, but it can also be triggered by Campi Flegrei in Italy, where the ground has been rising and falling for centuries due to underground gas movement and magma intrusion. In some cases, uplift of just a few centimeters per year has been enough to signal a pending eruption. But in the current scenario, the rates of uplift are much higher, suggesting an even more significant process at work. Additionally, there are concerns that these deep fluids might be interacting with underground fault systems in ways we don't fully understand. Many major fault lines are thought to be lubricated by fluid reservoirs, which can either stabilize the fault or, in some cases, trigger sudden slips. If the rapid rise of the landmass is altering the pressure dynamics along these faults, it could be setting the stage for future seismic events. Adding another layer of complexity is the possibility of unknown subsurface structures influencing the ground movement. Some geophysical surveys have suggested that the affected area may sit atop a hidden tectonic boundary, one that has remained dormant for millennia but is now showing signs of awakening. This could mean that we are witnessing the reactivation of an ancient fault system, or even the formation of a new one. What makes this situation even more puzzling is that similar patterns of uplift have been detected in multiple locations across the planet. Are these events connected? Could they be part of a larger, global phenomenon? Some researchers speculate that we may be entering a period of increased geological activity due to planetary-scale forces we have yet to fully comprehend. One possible explanation is that the Earth's lithosphere, the rigid outer shell of the planet, is undergoing a subtle but significant shift. Some models suggest that large-scale redistribution of mass, whether from melting ice caps, rising sea levels, or changes in Earth's internal heat flow, could be exerting new stresses on the crust. These stresses could, in turn, be triggering localized uplift in certain regions, while causing subsidence in others. The implications of such a shift are profound. If these changes are linked to deep Earth processes, they could have far-reaching consequences for everything from earthquake activity to ocean circulation patterns. Scientists are now racing to understand whether this is an isolated event or part of a much larger cycle, one that could reshape our understanding of how the planet functions. At the heart of this investigation is a fundamental question: are we witnessing a natural geological fluctuation, or is something more extraordinary occurring deep within our planet? The data we have so far suggests that whatever is happening beneath the surface is unlike anything seen in recent history. Whether this is a temporary anomaly or the first sign of a long-term transformation remains to be seen. Another angle scientists are investigating is the possibility of a deep-seated thermal anomaly, an unusual heat source rising from the mantle that could be driving both the rapid ground uplift and associated seismic activity. While magma intrusion is one possibility, there's another, lesser known but equally fascinating process at play: mantle plumes. Mantle plumes are upwellings of superheated rock originating deep within the Earth's mantle, possibly near the core mantle boundary. These plumes can rise over millions of years, gradually pushing against the lithosphere, weakening it, and in some cases, creating volcanic hotspots like those found in Hawaii or Yellowstone. If such a plume is developing beneath the affected region, it could explain why the ground is rising so rapidly. Evidence supporting this idea comes from recent geophysical scans of the area. Some researchers have detected unusual heat signatures at depths far below where typical tectonic activity occurs. These anomalies could indicate the presence of a thermal disturbance that is forcing the crust to expand and rise. This is particularly concerning because mantle plumes have been linked to some of Earth's most dramatic geological events, including large-scale volcanic activity, massive flood basalt eruptions, and even continental breakups. One of the most striking historical examples is the Deccan Traps in India. If enough portion of the crust becomes unstable, it could lead to regional earthquakes, fissures opening in the ground, and even the birth of new volcanic features. In fact, some geologists have noted that certain regions experiencing rapid uplift also show signs of increased volcanic gas emissions. This could indicate that magma is not only present but is actively degassing, releasing carbon dioxide, sulfur dioxide, and even traces of helium-3, a rare isotope that typically originates from deep within the Earth's mantle. The presence of helium-3 in significant quantities is often considered a smoking gun for deep mantle activity, as it is not commonly found in shallow crustal processes. But what makes this situation even more perplexing is the sheer scale of the deformation. The amount of uplift observed in recent months is more rapid than what would typically be expected from gradual geological processes. This raises a troubling question: could we be witnessing the early stages of a larger, more widespread geodynamic shift? One possibility being explored is whether this event is connected to global mantle dynamics. Some researchers propose that Earth's mantle operates in vast, interconnected cycles, where shifts in one region can propagate stresses and heat flow changes to distant parts of the planet. If this is true, then what is happening beneath this specific region may not be an isolated phenomenon, but rather a symptom of a much larger process unfolding deep within the planet. Historical records suggest that similar rapid uplifts have occurred in the past, though not always with catastrophic consequences. For example, parts of Scandinavia are still rebounding from the last ice age, a process known as post-glacial rebound, where land that was once weighed down by massive glaciers is slowly rising now that the ice has melted. However, post-glacial rebound typically occurs at a much slower rate than what we are currently observing. If the mantle plume theory holds true, it could mean that this region is on the verge of a major transformation. Some scientists speculate that, over time, continued uplift could reshape the local landscape, potentially leading to the formation of new volcanic structures or even causing sections of the crust to fracture and collapse. The question now is how fast these changes will occur, and whether they pose an immediate threat. If the uplift is being driven by a large-scale mantle process, then the timescales could stretch over thousands, or even millions of years. But if the forces at work are more volatile, such as a sudden release of magma or gas, it could mean that dramatic changes could unfold within our lifetimes. For now, the situation remains under intense scientific scrutiny. Researchers are deploying more seismometers, satellite-based ground monitoring systems, and deep Earth imaging technology to get a clearer picture of what is happening beneath the surface. The answers they find could not only help predict what comes next but also offer new insights into the dynamic and ever-changing nature of our planet. The concept of mantle plumes was first proposed in the 1970s by geophysicist J. Tuzo Wilson, and it's often compared to the idea of a mantle conveyor belt. While the majority of the mantle's material moves in a horizontal direction due to tectonic plate motions, mantle plumes work against this movement by rising vertically through the mantle. They form in regions of exceptionally high heat in the mantle, which is usually caused by radioactive decay of elements such as uranium, thorium, and potassium. These elements generate heat over time, creating localized areas of intense heat that slowly push upwards. One of the most striking features of a mantle plume is its scale. These plumes can stretch hundreds of miles across and extend deep into the Earth's mantle, sometimes all the way from the boundary between the Earth's outer core and the lower mantle. They are thought to rise through the mantle's convective currents, carving out channels as they move upward. Some plumes have been theorized to be so powerful that they can even influence tectonic plate movements or create hotspot volcanoes far away from active plate boundaries. For example, the Hawaiian Islands are believed to have been formed by a mantle plume. This stationary plume, sitting beneath the Pacific plate, has caused an ongoing series of volcanic eruptions over millions of years, forming an archipelago of islands in the Pacific Ocean. The plume remains fixed beneath the surface, while the Pacific plate moves across it, creating the chain of islands. Interestingly, the plume under Hawaii is not isolated. Similar structures exist beneath other regions, like Iceland, Yellowstone, and the Galapagos Islands, which are also associated with volcanic activity linked to mantle plumes. But it's not just volcanic islands that result from mantle plumes. These upwellings of molten rock have a profound impact on the tectonic plates they encounter. As the plume rises, it may interact with the Earth's crust, causing it to weaken or break apart. This can lead to the formation of rift zones, where the crust begins to pull apart, creating deep fissures or valleys. This process can also trigger earthquakes as the lithosphere is subjected to stress, disrupting the balance of tectonic forces. As the plume continues to rise, it can cause widespread surface uplift. The heat and pressure from below push the crust upward, potentially causing it to buckle or deform. In some cases, this can lead to dramatic changes in the landscape, such as the creation of new mountain ranges or the development of vast volcanic plateaus. For instance, the Deccan Traps in India, one of the largest volcanic features in the world, is thought to have been created by a mantle plume. This massive volcanic province erupted over thousands of years, releasing enormous amounts of lava and altering global climate conditions. While mantle plumes are thought to operate on geologic timescales, their effects on the Earth's surface can be quite dramatic over long periods of time. In fact, scientists believe that some of the largest mass extinction events in Earth's history could have been triggered, or at least exacerbated, by the effects of mantle plume activity. The end Triassic extinction, for example, is thought to have been linked to the eruption of massive flood basalts caused by a large plume in what is now the Atlantic Ocean. The resulting climate changes, caused by the release of carbon dioxide and other gases, may have contributed to the mass extinction of many species. It's also important to consider that mantle plumes are not solitary phenomena. They can have far-reaching effects on regional and even global tectonics. When a plume rises to the surface, the material in the plume can push against the surrounding tectonic plates, altering their movements. This can cause shifts in the Earth's lithosphere, creating new rift zones, mountain ranges, or even completely reorienting the tectonic plate boundary itself. This adds another layer of complexity to understanding the full scope of mantle plume impacts on the surface environment. Some geophysicists have even speculated that mantle plumes could play a role in the formation of supercontinents. As plumes rise and push against the overlying crust, they could eventually lead to the rifting of continents and the opening of new oceans. Over millions of years, these plumes could catalyze the processes that lead to the formation of massive landmasses, which eventually come together to form a supercontinent. The breakup of Pangaea, the supercontinent that existed millions of years ago, might have been influenced by the mantle plumes at the time. Given the potential impact of mantle plumes on the Earth's surface, it's crucial to understand how they may be contributing to the ongoing uplift and seismic activity in the region we're focusing on. Could a mantle plume be pushing against the crust and contributing to the rapid rise in the ground? It's certainly a possibility that researchers are exploring, especially when unusual heat signatures and seismic data suggest activity far deeper than the usual tectonic movements. If true, this could mean that the region is not only experiencing rapid deformation but also witnessing the birth of a new volcanic or rift zone that will dramatically reshape the landscape in the coming centuries or even millennia. The more scientists investigate, the more they uncover about how mantle plumes and their associated forces might be triggering profound changes on the Earth's surface. Whether this phenomenon is occurring in the region being studied or elsewhere remains uncertain, but the implications are enormous. As the Earth's mantle continues to stir beneath the surface, scientists are beginning to focus on more subtle yet equally significant features that could be contributing to the rapid rise in the region. One such feature is the role of crustal thinning, which could be a direct result of ongoing mantle plume activity or other deep-seated geological phenomena. When the Earth's crust becomes thinner in certain areas, it can become more susceptible to deformation. This deformation can manifest itself in a variety of ways, from the formation of deep valleys to large-scale surface uplift, similar to what is being observed in the region under study. Crustal thinning occurs when the underlying mantle exerts pressure on the overlying lithosphere. This pressure, often associated with mantle plumes or tectonic stresses, pushes upward on the crust, weakening it and causing the crust to spread out. As this happens, the material becomes more malleable and can begin to bulge. In some cases, this thinning process can eventually lead to large-scale faulting, resulting in fractures along the Earth's surface. These fractures, when they occur on a significant scale, can even give rise to new geological features like mountain ranges or rift valleys. When crustal thinning is coupled with the effects of a rising mantle plume, the results can be both dramatic and long-lasting. The region's surface may experience extreme changes as the crust becomes increasingly unstable and begins to rise rapidly. Over time, the thinning crust can lead to the formation of volcanic fissures, hot springs, and other geothermal features, further adding to the intensity of seismic activity. Geologists have observed this process in other areas of the world, such as the East African Rift and Iceland, where the thin crust is a direct result of underlying mantle plumes. As if this wasn't enough, there's another critical factor contributing to the rapid ground rise: the behavior of Earth's fault systems. The tectonic plates that cover the Earth's surface are not static. They're constantly moving, grinding, and interacting. Some of the most active and dynamic areas of the Earth are situated along fault lines, where these plates come together or drift apart. When the pressure exerted by mantle plumes and tectonic forces becomes too great, it can result in significant fault movement, causing the ground to either buckle or rise. Faults can be thought of as the seams in the Earth's crust. When the forces of plate tectonics cause these seams to break, it leads to earthquakes, but it can also trigger larger-scale uplift of the ground. An interesting phenomenon occurs when faults are coupled with magmatic intrusion. When magma from the mantle reaches the surface through these faults, it can add to the material already pressing against the crust, further accelerating the uplift process. This combination of forces, tectonic pressure and magmatic intrusion, has led to the formation of volcanic mountains, such as Mount St. Helens in Washington or Mount Vesuvius in Italy. The interplay between the forces at the Earth's surface and the dynamic movements occurring beneath it is what gives rise to some of the most violent and transformative events in Earth's history. Furthermore, as magma ascends through the Earth's crust and encounters pre-existing faults, it can create new pathways for future volcanic activity. The magma-filled faults often lead to the formation of magma chambers, and when these chambers become pressurized enough, they can lead to explosive eruptions. These eruptions can have massive, far-reaching effects, not only reshaping the landscape but also altering the atmosphere and global climate. While large eruptions are relatively rare, even smaller, ongoing volcanic activity can continue to modify the landscape and contribute to ground uplift over time. In the case of the region in question, if the combination of magmatic intrusion and fault movement continues, the ground could continue to rise, potentially at an accelerating pace. In fact, this could be the first signs of a larger geological event that could unfold over decades or centuries. If these forces persist and intensify, it could eventually lead to significant changes in the landscape, including the development of new mountain ranges or large-scale volcanic features. Another interesting factor to consider is the influence of nearby tectonic boundaries. In regions where multiple tectonic plates meet, the ground is often subject to multiple forces from different directions. These boundaries are notorious for being hotbeds of seismic activity, with earthquakes, volcanic eruptions, and land shifting occurring regularly. When a mantle plume is situated near a tectonic boundary, the effects can be even more pronounced. The interaction between the rising plume and the tectonic forces at the boundary could create a chain reaction that leads to further ground uplift, seismic activity, and other Earth-shaping events. It's also worth considering the longer-term implications of these geological processes. As mantle plumes rise and interact with the crust, they can cause a buildup of heat and pressure beneath the Earth's surface. Over time, this can lead to the gradual formation of large-scale volcanic or geothermal systems. These systems, while incredibly complex, have the potential to change entire regions, both geologically and ecologically. Volcanic eruptions, for example, can release enormous amounts of ash and gases into the atmosphere, influencing local weather patterns and even global climate. Additionally, these regions of active uplift can also experience frequent earthquakes, which further destabilize the area and could potentially lead to significant land subsidence in other regions. With rising ground and active tectonic forces, there is always the possibility of more seismic events that might add to the chaos. The tectonic boundaries in a region where magmatic activity is taking place play a crucial role in shaping the landscape, and understanding their dynamics can give us insight into why the ground is rising so rapidly in this particular area. These boundaries, where tectonic plates meet, are often sites of intense geological activity. There are three primary types of tectonic boundaries: divergent, convergent, and transform. Each type can influence the rising ground in different ways, with some of the effects being long-term and others causing sudden and dramatic changes. At divergent boundaries, tectonic plates are moving away from each other. As the plates separate, magma from deep within the Earth can rise up through the gap, creating new crust as it cools. This process is most commonly seen at mid-ocean ridges, such as the Mid-Atlantic Ridge, where the Eurasian and North American plates are pulling apart. However, divergent boundaries can also occur on land, where the movement of plates away from each other causes the formation of rift valleys. As magma wells up into these rift zones, it not only creates new crust but can also lead to localized uplift of the ground. This is a significant factor in areas like East Africa, where the East African Rift is actively pulling apart, causing the ground to rise steadily over time. The process of crust formation at divergent boundaries is often accompanied by volcanic activity. As the magma rises and erupts, it adds to the growing landmass and contributes to the continual rise of the ground in regions like Iceland, where volcanic activity at divergent boundaries is a major cause of ongoing land elevation. In regions where a mantle plume interacts with a divergent boundary, the process becomes even more intense. The mantle plume feeds additional magma into the rift, increasing the rate of uplift. This combined effect of the mantle plume and divergent plate movement creates a highly dynamic geological environment, which could explain the rapid rise of the ground in the region. On the other hand, at convergent boundaries, tectonic plates move toward each other. This can cause one plate to be forced under the other in a process known as subduction. Subduction zones are often associated with some of the most intense geological activity on the planet, including earthquakes, volcanic eruptions, and mountain formation. When one tectonic plate dives beneath another, it causes immense pressure to build up, which can eventually lead to the formation of volcanic arcs. These arcs are chains of volcanoes formed by the rising magma from the subducting plate. The Andes Mountains, for example, are the result of the subduction of the Nazca Plate beneath the South American Plate. Movement of tectonic plates at convergent boundaries is not only responsible for volcanic activity but can also lead to the uplift of massive mountain ranges. The collision of two plates can cause the crust to fold and buckle, creating towering mountain ranges like the Himalayas, which continue to rise as the Indian Plate collides with the Eurasian Plate. This process can also generate earthquakes and massive fault lines, which can destabilize the surface and lead to rapid ground displacement. If the tectonic activity in the region is occurring at a convergent boundary, we could expect not only volcanic activity but also the formation of a mountainous landscape, further contributing to the rising ground. Transform boundaries, where two plates slide past each other horizontally, are perhaps the most unpredictable in terms of surface uplift. While these boundaries typically don't create volcanic activity, they are highly prone to earthquakes. When the plates slide against one another, they can become locked due to friction, causing a buildup of pressure. When the pressure finally releases, it can result in a massive earthquake that can shake the surrounding region, causing the ground to rise or fall in an instant. The San Andreas Fault in California is a prime example of a transform boundary, and the area has experienced numerous large earthquakes due to the movement of the Pacific and North American plates. The effects of transform boundaries on the rising ground are somewhat different from those of divergent or convergent boundaries, but they can still play a significant role in shaping the landscape. When earthquakes occur along transform faults, they can cause land uplift along fault lines. This uplift can occur in small sections but can be significant enough to impact the overall landscape. In regions with multiple fault systems interacting, this uplift can become widespread, contributing to the rapid rise of the ground over time. In regions where tectonic boundaries overlap or are located in close proximity to one another, the forces of divergent, convergent, and transform plate movements can all come into play. The result is a complex and highly dynamic environment, where the forces from multiple tectonic boundaries are interacting with each other. This can cause a variety of geological events, from massive volcanic eruptions to earthquakes and land uplift. The combined effects of these movements can cause significant changes to the Earth's surface over relatively short periods of time, with some regions experiencing dramatic ground rise as a result of these ongoing forces. Another important factor to consider is the influence of tectonic boundaries on the formation of large fault systems. In regions where multiple tectonic plates meet, the crust is often broken into a series of interconnected fault lines. These fault systems, such as the ones found in the Pacific Ring of Fire, are hotspots for seismic activity, with regular earthquakes and volcanic eruptions occurring as a result of the movement of the plates. These fault systems can be highly complex, with multiple faults interacting with one another. As the pressure builds along these fault lines, it can lead to the sudden release of energy, causing the ground to shift and rise rapidly. As tectonic movements continue to reshape the landscape, we can also look deeper into the long-term implications of plate interactions. Beyond the immediate effects of volcanic eruptions and earthquakes, the movement of the Earth's plates has the potential to trigger even more significant transformations over millennia. For instance, tectonic plate motion is a key driver of the Earth's geological evolution, which ultimately influences everything from the rise of mountains to the configuration of continents. One area that continues to intrigue geologists is the role of superplumes beneath the Earth's crust. These enormous upwellings of hot mantle material can have a profound effect on tectonic processes. Superplumes are believed to rise from deep within the Earth's mantle, often beneath major tectonic plates, and contribute to the formation of large volcanic hotspots and rift zones. When superplumes rise towards the surface, they cause the lithosphere to weaken and stretch, making it more susceptible to faulting and displacement. In some cases, superplumes may even be responsible for the formation of large continental rifts. One example is the East African Rift, which has been slowly pulling the African continent apart for millions of years. Geophysicists suspect that a superplume beneath the region is adding heat and pressure, forcing the tectonic plates to move apart. Over time, this process has led to the formation of rift valleys and increased volcanic activity. The rising of the ground in such regions can be attributed, in part, to these deep-seated mantle processes. Interestingly, superplumes have the potential to change the way we understand the Earth's tectonic cycles. Some researchers have proposed that these massive mantle upwellings could be the driving force behind periods of accelerated plate tectonics. During these times, the Earth may experience an increase in the frequency and intensity of earthquakes, volcanic eruptions, and rapid ground rise. When a superplume is at its peak, the heat and pressure it generates can cause the crust to become more dynamic and unstable. This leads to heightened geological activity at the surface, which can result in regions experiencing rapid shifts in elevation, much like what we are observing today. A notable example of this is the Hawaiian Islands. While they are located in the middle of the Pacific Plate, away from tectonic boundaries, their formation can be attributed to a stationary mantle plume. The plume has remained in the same location for millions of years, creating a series of volcanic islands as the Pacific Plate slowly moves over it. Each eruption has added layers of new material to the surface, raising the islands above sea level. Over time, this process of continuous volcanic activity has caused the islands to rise higher and higher, with some areas now sitting thousands of feet above the ocean. But superplumes don't only create volcanic islands, they can also influence larger-scale tectonic changes. For example, when superplumes are active, they can destabilize the surrounding plate boundaries, leading to the formation of massive cracks or faults in the Earth's surface. These cracks often lead to the formation of new tectonic boundaries and, in some cases, the creation of new oceans. A prime example of this process is the opening of the Atlantic Ocean, which began as the superplume beneath the supercontinent Pangaea forced the crust apart. Over millions of years, this process continued, eventually creating the rift that formed the ocean as we know it today. Now, with the ground rising rapidly in certain regions, it's possible that we're witnessing the early stages of a new tectonic cycle. The interaction of superplumes with the surrounding tectonic plates could be sparking new zones of active rifting, which could lead to dramatic shifts in the global landscape. In some regions, the rise of the ground may be just the beginning of a much larger tectonic event that could alter the continent's shape and configuration. The slow and often imperceptible movement of the Earth's plates may be gearing up for something far more explosive in the future. Additionally, the connection between tectonic movements and the rise of the Earth's crust is not always immediate. Sometimes, the effect of a shifting plate or a mantle plume can take thousands, or even millions, of years to show visible results on the surface. This delayed response is due to the immense pressure and heat generated beneath the Earth's crust. Over time, this pressure causes the crust to slowly stretch and deform, eventually leading to the formation of features like mountain ranges, fault lines, and rift valleys. In some cases, the ground rise we are witnessing in certain regions may be the result of these slow, long-term processes that have been in the works for centuries, or even longer. Looking beyond just plate tectonics and mantle plumes, it's worth considering the impact of deep-seated geological features like mountain roots. When massive mountain ranges form, such as the Himalayas or the Andes, the underlying tectonic activity doesn't stop once the surface peaks have been formed. The roots of these mountains extend deep into the earth, exerting a significant influence on the surrounding crust. These mountainous regions are often in a constant state of flux as they slowly adjust to the pressure beneath them. Mountain roots act as a counterbalance to the forces at play beneath the surface, pushing the crust upwards as the plates collide. This constant push and pull between the surface and the depths of the earth results in both gradual and sudden surface changes. The rising of the ground in some areas could be the result of such movements beneath the Earth's surface, which are not always visible or easily detected by conventional means. When combined with the power of mantle plumes and tectonic plate movements, the formation and ongoing adjustment of mountain roots can lead to significant and rapid ground rise in some regions. While the forces at play are often so deep within the Earth that they are not immediately perceptible to us on the surface, the results can be dramatic. Over time, these forces may lead to the formation of new mountain ranges or the uplifting of existing land masses. Furthermore, the interaction between these geological forces and surface processes like erosion can contribute to even more rapid changes. As mountains rise, the forces of wind and water erosion begin to chip away at their peaks, slowly wearing them down. However, the deeper roots of the mountains continue to push upwards, maintaining their elevation. In some cases, this constant back and forth between uplift and erosion leads to the formation of extraordinary geological features, such as towering cliffs or ridgelines that appear to rise from nowhere. These features can appear almost overnight in geologic terms, providing us with a glimpse into the immense forces shaping the Earth beneath our feet. As we explore the tectonic forces at work beneath the Earth's surface, it becomes clear that the mechanisms driving ground rise are far more complex than simply the shifting of plates. The interplay between mantle plumes, superplumes, mountain roots, and tectonic activity creates a dynamic and constantly changing geological environment. Continuing with our exploration of tectonic movements and the forces shaping the Earth's surface, it's important to consider how these changes aren't just isolated to specific regions. The entire globe is interconnected in its geological processes, and a shift in one part of the world can have ripple effects elsewhere. As we observe rapid ground rise in certain areas, these events could potentially be tied to larger-scale shifts occurring in more distant regions. For example, in places where mantle plumes are especially active, such as beneath the Pacific Plate or the African Plate, we can see how a localized upwelling of magma can contribute to widespread tectonic activity. These plumes can trigger a chain reaction of movements, causing nearby faults and plate boundaries to shift in response to the stress being applied beneath the surface. When one section of a tectonic plate begins to rise rapidly, it can disrupt the stability of neighboring sections, leading to a ripple effect of seismic activity and crustal movement. One thing that is often underestimated is the deep-seated interaction between tectonic movements and the Earth's magnetic field. The Earth's magnetism plays a crucial role in the movement of charged particles within the Earth's outer core and even influences the mantle's behavior. Though this may not be directly visible on the surface, the magnetic forces interacting with the tectonic plates can affect the manner in which these plates move. Studies in geomagnetism have shown that there are strong links between Earth's magnetic field reversals and tectonic shifts. During periods of geomagnetic reversals, when the North and South poles swap places, the Earth's magnetic field experiences fluctuations that could influence the convection currents within the mantle. These currents, which help to drive plate tectonics, could become more erratic during these periods, potentially contributing to more rapid shifts in tectonic plates. While the mechanics of this interaction remain unclear, it's worth considering that magnetic anomalies might be contributing to the rise and fall of certain regions, especially those located near tectonic boundaries. As we focus on the broader implications of this global movement, the concept of tectonic dominoes comes into play. This theory suggests that when one region experiences significant seismic or magmatic activity, it can trigger a cascade effect, resulting in other regions experiencing similar ground shifts. It's a little like pushing over the first domino in a chain. Once one area is destabilized, the underlying forces can spread outward, triggering additional ground rises and shifts elsewhere. A notable historical example of this can be seen in the Pacific Ring of Fire, a hotspot for volcanic and seismic activity due to the concentration of tectonic plate boundaries in the region. The area experiences a continual domino effect, as seismic events and volcanic eruptions in one location often lead to aftershocks or tectonic shifts in surrounding regions. This is part of why earthquakes and volcanic eruptions are so common along this belt. If a significant earthquake occurs in one place, the forces of the Earth's crust are often transferred to nearby regions, leading to a higher likelihood of ground shifts or volcanic activity in those areas. Understanding how these interconnected systems function is crucial in comprehending the larger picture of rapid ground rises. While some areas might experience rapid changes due to localized events like volcanic eruptions or deep-seated magma activity, the ground's rise in one region may also be a response to distant tectonic shifts. This connectivity means that a major event in one area could set off a chain of seismic activity that might alter the ground in distant regions. The immense interconnectedness of Earth's tectonic and geological systems makes it difficult to predict exactly how any one event will affect others, but it also reinforces the need for careful monitoring and analysis of the planet's activities. Interestingly, the impacts of tectonic shifts don't stop at the geological level. When tectonic plates move, so too do the ecosystems on top of them. Rapid ground rises, shifts, and volcanic eruptions can completely alter the landscape, creating new environments and ecosystems while destroying older ones. In some cases, these dramatic changes have a profound effect on the biodiversity of affected regions. Species that once thrived in a particular area may suddenly find their environment uninhabitable, while new species may emerge to adapt to the altered conditions. This change in ecosystems is not just a brief, temporary event, it's a fundamental shift that can take centuries to fully stabilize. As tectonic shifts cause mountains to rise and valleys to sink, new habitats are formed, and new ecological niches become available. Over long periods, these changes can lead to the emergence of entirely new ecosystems, as plants and animals evolve to adapt to the changing environment. Some of the most fascinating aspects of this process are the unexpected ways in which organisms adapt to extreme geological changes. For example, After a volcanic eruption, the barren landscape may slowly become populated by pioneering species that thrive in the nutrient-rich soil left behind by the eruption. Additionally, as the Earth's surface continues to shift and rise, the presence of natural resources changes. We often associate oil, gas, and mineral deposits with specific geological formations, and these resources are closely tied to the movements of the Earth's crust. The rise of new landmasses, often due to tectonic activity, can expose new reserves of these materials, providing opportunities for extraction. At the same time, the movement of plates can also result in the subduction of materials, which can lead to the depletion of some resources in certain regions. The discovery and extraction of these resources are often shaped by tectonic movements, with geologists constantly searching for new deposits in regions where ground rise is occurring. This means that the rising ground we see today may hold the key to new resource discoveries in the future. Whether it's the potential for new mineral deposits, the discovery of valuable oil reserves, or the extraction of geothermal energy from recently exposed volcanic zones, tectonic movements play a critical role in shaping the economic and environmental landscape. As the Earth continues to evolve, the forces driving ground rise and tectonic shifts will remain a key factor in the ongoing changes to the planet's surface. The next steps in understanding and harnessing these processes lie in uncovering the mysteries of how magma, mantle plumes, and plate tectonics work together to shape the world we live in. By continuing to study these phenomena, scientists will unlock even more secrets of our planet's dynamic and ever-changing nature. As we continue to explore the complex and dynamic nature of the Earth's movements, it's essential to dive even deeper into how these tectonic forces interact with one another. One of the critical aspects of this interaction is the behavior of the Earth's lithosphere, the rigid outer layer of the Earth, and its role in shaping the surface of the planet. The lithosphere, composed of both the crust and the uppermost part of the mantle, is divided into large, tectonic plates that float atop the semi-fluid asthenosphere. These plates are constantly in motion, driven by forces such as mantle convection, slab pull, and ridge push. As these plates move, they interact with each other at their boundaries, resulting in various geological phenomena, including the formation of mountains, earthquakes, and volcanic eruptions. One of the most significant features at tectonic plate boundaries is the creation of fault lines. Fault lines are fractures in the Earth's crust that allow for the movement of tectonic plates. When two plates slide past each other, as in the case of transformed faults, or collide, as in convergent boundaries, immense stress is generated along these fault lines. This stress can build up over time, resulting in earthquakes when the energy is released in a sudden jolt. These movements not only affect the land above but can also create massive shifts beneath the surface. The depth at which these tectonic shifts occur can also play a significant role in how they impact the surface. Shallow earthquakes, for example, tend to cause more damage to infrastructure and human populations due to their proximity to the Earth's surface. In contrast, deep-focus earthquakes, which originate much deeper within the Earth, can still trigger significant geological changes but may be less destructive to surface-level structures. Understanding the depth and location of tectonic shifts is crucial for predicting potential hazards and assessing the risk to regions affected by rising ground. Interestingly, as the ground rises in certain areas, it's not just the tectonic plates and the forces of magma pushing up from below that are at play. The Earth's internal processes, including the movements of molten rock, can be influenced by external factors, such as the gravitational pull of the Moon. The tidal forces exerted by the Moon's gravity cause the Earth's surface to experience slight bulges and deformations, which in turn can affect tectonic movements. This is a subtle yet important aspect to consider when looking at how the ground rises in various regions, as even small variations in the Earth's gravitational forces can influence seismic activity and the behavior of tectonic plates. As we continue to investigate these shifts, it's also important to consider the role of human activity in exacerbating or mitigating the effects of tectonic movements. For example, activities such as mining, drilling for oil, and geothermal energy extraction can sometimes trigger seismic events. By removing large amounts of material from the Earth's crust, we are altering the balance of pressure on the tectonic plates, which may contribute to the rising ground or induce earthquakes in certain regions. This has raised concerns among experts who are exploring how human intervention is affecting the natural seismic activity of the planet. It's also important to consider the impact that human infrastructure can have on tectonic movements. In areas where large-scale urban development is taking place, the construction of dams, roads, and buildings can lead to a phenomenon known as induced seismicity. This occurs when human activities alter the stress in the Earth's crust, causing earthquakes or land shifts. A well-known example of this is the 2011 earthquake in the United Kingdom, which some researchers believe was triggered by the extraction of gas from the ground. As the Earth's crust is altered by human activities, the stresses along fault lines can become more pronounced, leading to more frequent and intense tremors. This interplay between human activity and natural geological processes highlights just how interconnected the Earth's systems are. While tectonic shifts, magmatic activity, and mantle plumes are naturally occurring events, human actions can exacerbate or modify these forces, potentially influencing the extent and frequency of ground rise or seismic events. As urbanization and resource extraction continue to expand across the globe, understanding the relationship between human intervention and the natural world becomes even more critical for mitigating risks and ensuring the safety of populations living in areas prone to tectonic activity. Looking forward, one of the challenges facing scientists is accurately predicting when and where these rapid ground rises and seismic events will occur. While advancements in seismology and geophysics have provided us with the tools to monitor the Earth's movements in real time, predicting these events with precision remains elusive. The unpredictable nature of tectonic shifts makes it difficult to forecast when and where significant ground rise will take place, leaving us to rely on early warning systems and preparedness plans to respond to these changes. To improve our understanding of tectonic processes, researchers are developing more sophisticated models of the Earth's interior. By using advanced techniques such as seismic tomography, which allows scientists to create three-dimensional images of the Earth's interior, researchers are gaining a clearer picture of how the mantle and crust are interacting beneath our feet. These models provide invaluable insight into the complex forces at play, helping scientists make more informed predictions about where tectonic movements may occur and how they might impact the surface. Additionally, the study of satellite imagery and remote sensing technology has proven to be a game changer in tracking ground movements. Through techniques like InSAR, interferometric synthetic aperture radar, scientists can observe even the smallest movements of the Earth's surface with remarkable precision. These technologies allow for the monitoring of regions that are difficult to access or have limited infrastructure, providing real-time data on ground shifts and seismic activity. In conclusion, the rapid rise of the ground in certain regions is the result of a complex interplay of geological forces, including tectonic movements, magmatic activity, and mantle plumes. As we continue to study and monitor these events, it's clear that the Earth's surface is constantly evolving. Whether triggered by deep-seated tectonic shifts, magmatic pressure, or human activity, the forces driving these changes are powerful and far-reaching. Understanding these phenomena is essential for predicting and mitigating the impacts of ground rise and seismic events, ensuring the safety and preparedness of populations living in affected regions. As we continue to unlock the mysteries of the Earth's interior, our knowledge of how these shifts shape the world around us will only deepen, providing invaluable insight into the dynamic forces at play beneath our feet.